My name is Jonah Wade, and this is Physics 2 Lab 5. Let's just jump into the table of contents. So, first, we're going to go over some basic physics concepts as well as some important formulas. Then, we're going to go over the setup and experimental data and go over some checkpoint questions. Next, we'll look at some excerpts from code, then to discuss the program output and computational model. And lastly, we'll interpret some simulation questions and answer some additional questions as well.
So the models and fundamental physics principles used in this experiment are on the screen now. The first and second experiment help to describe the magnitude of the magnetic dipole and calculate the magnetic dipole moment. In the third experiment, n is a -3, and the fourth experiment shows the magnetic field due to a dipole at any location, and that is what's known as the Biot-Savart law. So the results of this experiment were found that the magnetic dipole moment was 1.01 am squared. The magnetic field proportional to the distance was -3.5. The experimental B net was -3.123 e to the -5, 2.727 e to the -5, 0, and the experimental B net, or the absolute value of that, was 4.775. So this experiment itself is done by first downloading a magnetometer app onto a smartphone, and you're going to adjust the phone until the magnitude, or Bx, is facing north, and Bx is 0. Then you're going to place a meter stick perpendicular to the width of the phone, and then you're going to find a sensor on the magnetometer, or find the sensor of the magnetometer on the phone. And so to do this, you're going to slide the phone perpendicular until the X component is at its max, and then you're going to place the piece of tape at that width. And then you're going to rotate the phone 90 degrees inside the phone until the Y component is at its max, and then you're going to place a tape there as well. And then the intersection of the tapes is the location of the sensor of the chip. And so moving on to the first portion of this experiment, we're going to find the distance between the sensor and the magnet, where Bx equals 20 Teslas. And then you're going to do that twice, and then you're going to do this step for 70 nanoteslas, 120, 170, and 220. So from this experiment, as you can see, the data is on the screen. And to calculate the slope of n, we took the natural log of both sides, and it was found to be -3.5, which is a bit above the predicted -3. Here you can see my calculations on the screen. Now, next step of the experiment was to find the d-perp, or the distance perpendicular, where the magnetic field was 100 nanoteslas. Oops. So then you're going to record the Y component at this location. Then you're going to align a second ruler perpendicular to the first and in line with the sensor, and move the phone along the second ruler until the D is equal to d-perp. Then you're going to record X, Y, and Z and the value of By, and then you're going to repeat the steps twice and record the data. Here is my data on the screen. As you can see, I found an experimental B net of 3.123 e to the -5, 2.727 e to the -50, and the absolute value of B net to be 4.775. Some observations that I found during this experiment were that the X component increased as the magnetic field increases, that B Earth should only be subtracted from the Y component, and when the magnetometer is far away from the X-axis, the magnetic field in the X direction is almost 0. In this experiment, there were also some assumptions made. The first one being that there is no external magnetic field acting on the system other than the magnet, which is likely not true, and the initial Bx of the lab was assumed to be 0. Moving on to the coding portion of this, as you can see, my coding is split up into 2 slides. And to describe basic rundown, I first created a dipole B, which is